Hello, this is JNotz. Welcome to the instructional video for AP Chemistry titled Calorimetry of Chemical Reactions. You'll need a copy of the video guide, a calculator, and something to write with. I have two goals for you today. One is to review an important thermochemical concept from your hand warmer lab, which you should have already completed. And two, to apply your existing knowledge about calorimetry to a new situation, the energy of a chemical reaction. To start out, what I'd like for you to do is to answer the question, where does the heat come from? In the hand warmer that you designed. Use the diagram below to assist you as you write out your answer. Pause me while you think and write. Now let's check your answer. You should have explained the formation of a solution in 3 steps, each with its own exchange of energy. Step 1 involves separating the solute particles from each other so that they may interact with the solvent. This step is always endothermic because it involves breaking attractive forces between the particles. Step 2 is very similar to step 1 in that it also involves a separation of particles from each other. This time it's the solvent particles that have to expand, but still attractive forces are being broken, just like in the case of the solute. So because we're breaking attractive forces, again, this process is also endothermic. Finally, the third step in the process is the attraction between the solute and solvent particles in step 3. This step is exothermic because it involves the formation of attractive forces between particles. Let me re-emphasize these points again. Whenever attractive forces must be broken, as in step 1 and step 2, the heat exchange must be an endothermic process. Now, in order for attractive forces to form, heat will always be released, and this will be an exothermic process. So, in a situation where a salt's being dissolved in water, what makes the difference between some salts that have an overall exothermic dissolve versus others that have an endothermic dissolve is the relative sizes of the energy exchanges that are happening in the 2 endothermic steps versus the exothermic step. Remember that you're trying to answer the question, where does the heat come from in the hand warmer lab? So let's look at this process in terms of comparison of the 3 enthalpy values for the 3 steps. First of all, we have delta H1 and delta H2 for the 2 endothermic parts of the process. This means that heat is going to be absorbed whenever the solute particles pull away from each other and the solvent particles pull away from each other. We also have the enthalpy change for the 3rd step, and this is exothermic. Heat is released because instead of pulling particles away from each other, we're allowing new attractions to form. Now, because the whole point of the hand warmer lab was to find a salt that gave a highly exothermic dissolve, we then know that the magnitude of the energy change for step 3, the exothermic step, had to be significantly greater than the magnitude of the energy change for the other 2 steps. And that's why the salt released energy overall as it dissolved. I'd like you to answer one more question before we move on to the new material. Take a look at the diagrams at the top of the next page and decide which one shows an endothermic dissolving process, and which one's illustrating an exothermic dissolving process. Also, just to finish up here, I'd like you to think about one last question related to solution formation. Chemists often classify the formation of a solution as an ambiguous change. In other words, not purely physical nor chemical. So I'd like you to think about why it is that they might say that, and check back in with me after you've finished thinking about these questions and jotting down your answers. Hopefully you noticed while you were looking at the diagrams that they do share some features in common, and then they have some things that are different. One thing they have in common is that they both show very clearly that steps 1 and 2 of the solution formation are endothermic processes. It requires energy. Energy must be absorbed in order to break the attractive forces in the solute and in the solvent. Another thing that they have in common is they both show that the energy involved for step 3 is an exothermic process. In other words, energy is released as step 3 occurs, as the attractive forces are formed between solute and solvent. Now, the way that these diagrams are different also helps you to differentiate between the endothermic versus the exothermic diagram. This first diagram here, diagram A, is the exothermic case of solution formation. And the way that you can tell is that the exothermic arrow is a greater magnitude than the endothermic arrow. There is more energy released when this solution forms than there is absorbed. So overall, it's an exothermic dissolve, and it would be a good choice for a hand warmer. For diagram B, this one should be labeled endothermic because it shows just the opposite. It shows that more energy has to be absorbed to get steps 1 and 2 to occur as compared to how much gets released when step 3 happens. So overall, the dissolving of that salt comes out as an endothermic process. The sum of all 3 steps is a net absorption of energy. And this kind of a salt wouldn't be useful for a hand warmer, but it could be used in another application, perhaps a cold first aid pack. And the final question here at the bottom, why would we term a solution formation process as ambiguous? Well, hopefully you've realized that it does have some characteristics in common with a chemical reaction. It has the process of attractive forces being broken and then new attractive forces forming. This is very similar, runs very parallel to, in a chemical reaction, chemical bonds being broken in the reactants and then new chemical bonds forming in the products. And just as the attractive forces here, when they break, that requires energy. When we break chemical bonds, that also requires energy. And similarly, when the attractive forces between solute and solvent form, that is a release of energy. That's an exothermic process, just as chemical bond formation is also exothermic. But at the same time, we know that a solution formation is simply the formation of a mixture. We don't have a new chemical substance being formed here. We can physically separate this mixture back out into its original components. So since it shares some characteristics in common with a chemical reaction and others with a physical change, we term this as an ambiguous process. Speaking of chemical reactions, I'd like to go ahead now and move on to part 2, which is the extension of calorimetry to a chemical reaction. What I'd like you to see here is that many of the things that you already know about the calorimetry of solution formation can be applied to the calorimetry of a chemical change. Let's take a look at number 61 together, and I will show you how to set this problem up and solve it. In a coffee cup calorimeter, 50 milliliters of 0.1 molar silver nitrate and 50 milliliters of 0.1 molar hydrochloric acid are mixed to yield the following reaction. And we can see here the net ionic equation for the precipitation reaction between silver ions and chloride ions to form the solid silver chloride. The two solutions were initially at 22.60 degrees Celsius, and the final temperature is 23.40 degrees Celsius. Calculate the heat that accompanies this reaction in kilojoules per mole of silver chloride formed. Assume that the combined solution has a mass of 100 grams and a specific heat capacity of 4.18 joules per degree Celsius per gram. First of all, let's get the big picture. We have a chemical reaction that's going on inside this coffee cup calorimeter. We start out with two aqueous solutions. We have silver nitrate solution and hydrochloric acid solution. And then they're going to be mixed together and a precipitate's going to form, namely the silver chloride. The parallel that I'd like you to see here with the chemical reaction compared to solution formation is that initially, before these two solutions are mixed together, the compound is very soluble in the water, meaning that the silver ions are solvated by water molecules, surrounded and dissolved by water molecules, and so are the nitrate ions, surrounded and dissolved, solvated by water molecules in our solution. And in the other solution, we have a similar thing going on with the hydrogen ions being surrounded by water molecules and the chloride ions as well. But now, once those solutions are mixed, those attractive forces between the silver ions and water molecules are going to have to break. And similarly, the attractive forces between the chloride ions and the water molecules are going to have to break, because now those two ions are going to attract to each other and form a new attractive force in the precipitate silver chloride. So just like solution formation, we have attractive forces being broken. That's going to be an endothermic process. And we have new attractive forces being formed. That's going to be an exothermic process. And the data from a calorimetry experiment can tell us whether or not this chemical reaction came out to be overall an exothermic reaction or an endothermic chemical reaction. Now let's go ahead and start setting up the problem a little bit more specifically here. All right, first of all, we're going to need to figure out what kind of a mathematical approach we're going to need to take here. Well, we know that the key to a calorimetry problem is through the change that the surroundings are experiencing. That's how we figure out what's going on with the system. We can't access this system directly. This system is the actual chemical reaction, the bond breaking and the bond forming. We have to watch what happens to the surroundings in order to figure out or infer what was happening with our system, our chemical reaction. So the first step you're going to make is you're going to find out what was our heat energy involved for our surroundings. This might be an absorption, it might be a release. We're just going to have to look at the data to figure that out. But regardless, to find this heat energy for the surroundings, you're going to use this formula. Mass times specific heat times the change in temperature. And as always, remember that your delta T is always final minus initial. The surroundings for these types of problems is the solution itself, just like it was for the older calorimetry problems with the solution formation. So we can plug in everything that we know about our solution, our chemical solution. The mass is 100 grams. The reason why they tell us that is because the volume of the two solutions here adds up to 100 milliliters, and we're going to assume that the density is equal to 1 gram per milliliter because it's mostly water. So that's where they got that 100 grams. Okay, and the specific heat, along those same lines, they give us the specific heat of water. You might recognize that number. Because again, the solution that you're combining, the solutions that you're combining are mostly water. So we'll just substitute the specific heat of water to use here. It's not much different from reality. And then our delta T. We need final minus initial. So we're going to need to do the final temperature, 23.40, minus the initial, 22.60. And that gives us a difference of 0.80 degrees Celsius. And so our change, or I should say our energy quantity that our surroundings is experiencing is a positive value, meaning our surroundings is experiencing an increase in heat energy. It is absorbing energy. When I do the math on this, I'm getting 334.4 joules absorbed by the surroundings, the solution itself. This means that the chemical reaction must have given that heat off. The chemical reaction itself is exothermic. More energy was released when the new bonds formed as compared to the amount absorbed when the old bonds broke. So now what we can say, since heat lost equals heat gained, or rather I prefer to say heat absorbed equals heat released, then we can say that the heat for the system, which is the chemical reaction, is a negative 334.4 joules. In other words, the chemical reaction itself gave off that much energy. We are dealing with an exothermic reaction. Okay, so that's the main point of the problem right there, is to figure all of that out from what's given, set it up and solve, and critical to remember that the surroundings gives us the insight into what's happening with the system. Now, the last thing you're going to need to do with this problem is basically just a game of unit conversion. They want their answer to be written in kilojoules per mole of silver chloride formed. So you're going to need to just find out how many kilojoules you've got and divide it by how many moles of silver chloride you formed, and you'll have it. All right, well, the joule to kilojoule thing, that'll be really easy. That's just moving the decimal. So that's how many kilojoules our reaction released. Now, that said per mole of silver chloride formed, so we're going to need to go back up here to the top and take a look at our amounts and our stoichiometry. All right, so let's see here. We've got 50 milliliters of 0.1 molar silver nitrate, and we have the same amount in molarity for the acid. So what that's going to mean is that we have 5 times 10 to the negative third moles of the silver ion that's participating in the reaction. And we also have the same moles, 5 times 10 to the negative third moles of chloride ions participating in the reaction. They react in a 1-to-1 ratio, and they produce the precipitate in that same ratio. So that means that we're going to also produce 5 times 10 to the negative third moles of silver chloride. And that's really the number we're after for our denominator in our final answer right there, because that's what the problem specified. Okay, let's go back down and look at those numbers and plug it in. What we're really solving here is the heat of reaction, our enthalpy of reaction. And that's going to be negative 0.3344 kilojoules of heat released in this reaction for every 5 times 10 to the negative third moles of precipitate, silver chloride, produced. All right, and then we're going to divide it out, and we get about negative 67 kilojoules for every mole of silver chloride, to 2 significant figures. Now, you might have noticed at the top, the answer that the textbook gives is 1 off from mine, negative 66 kilojoules per mole. But that's not to worry, because they probably just rounded within their answer, within their work as they went, whereas I didn't round until the very end. As long as you understand the setup, that's the main thing. Those little differences in answers aren't to be stressed over. All right, now I think I'm going to call it quits right there. There are 2 more practice problems in this video guide, but I've already talked for more than 15 minutes, and I can't expect anyone to pay attention for longer than that, especially in this format. So we'll stop there. Please think about what questions you might have for me. I'll give you some time in class tomorrow to ask those questions, and I'll also give you some time to try some of these calorimetry problems on your own or in small groups, and I will be happy to assist you with the setups as needed. Also, at the end here, there should be a few quick little checking for understanding questions that I'd like for you to answer, just so that I can see how I did here and how you did. And I appreciate, finally, the time and the effort and the attention that you've given to viewing this instructional video. I hope that it was helpful for you, and I will see you in class tomorrow. Bye-bye.